Team 2, and our presentation is on energy use and cost optimization in a factory setting. The presentation will be broken up into 5 parts. First, the system overview, then each subsystem, then the mathematical modeling, solution, and explanation. The function is to minimize energy cost in a plant while maintaining product output, worker comfort, and unit production cost. The system contains 3 subsystems: machine and process operations, which includes workers and machines used in production; HVAC and climate control, which controls plant heating, cooling, and humidity; and lighting, which includes lighting fixtures of all kinds. For system inputs, we have electricity; for outputs, we have energy cost; and for our shared variables, we have energy costs and time of operation. Our system is limited to the manufacturing facility while workers are present. Manufacturing accounts for more than a quarter of the energy usage in the US. Facilities on average use 95.1 kilowatt hours per square foot every year. One factory uses as much power as 143 homes on average every year. Energy cost reduction helps with company profitability and sustainability. Our system flow diagram, which shows the system boundary, system objective, our shared variables, inputs and outputs, and our 3 subsystems as mentioned earlier. Each subsystem has its objective, inputs and outputs, and design variables.
Hello everyone, I will be presenting our work on Subsystem 1, Machine and Process Operation. The goal is to optimize the velocity of each factory machine while maintaining the electricity cost and get the target production output through an optimization model in MATLAB. The electricity costs are a significant factor in automated manufacturing. Optimizing robot operation can help reduce cost while ensuring production targets are met. Let's define the problem. The energy cost is 1841 cents per kilowatt. We have 2 types of robots with different masses and power consumption. Time available to operate is 40 hours. Our design variables are the velocities of robots of each type. To model energy consumption, we use these equations, where energy consumption is a function of the robot's mass, velocity, and power consumption factor. The production rate is calculated based on the robot's speeds per unit. The total production output depends on the robot's speeds and time available to produce. We set as our constraints to ensure feasibility of the robot's movements and meet the production requirement of at least 500,000 units.
The design trade-offs and modeling approach. The variables under consideration are velocity 1 and velocity 2. The trade-offs are such that each machine's mass, efficiency, production rate, and achievable velocities are different. The machine with the higher mass has a higher production rate output, higher velocity, but lower efficiency. The production output depends on the velocity of the machinery. The optimization method was determined that it was a constrained nonlinear programming problem. We used MATLAB's fmin_con function, where we changed the initial values 5 times and resulted in an optimal velocity of 3.5 for V1, 2.83 for V2. This resulted in a total energy cost of $7,247.50 per week.
My name is Winter Williams, and I will be covering Subsystem 2 HVAC controls optimization. Just some background. HVAC energy consumption accounts for roughly 30 to 45% of the total electricity usage for most commercial buildings. You'll notice in the chart to the right that HVAC is a significant driver for the amount of electricity that's going to be used for most commercial buildings throughout their year. Roughly 95.1 kilowatts of electricity and 130 kilowatts of natural gas per square foot are used for HVAC each year. Thus, the HVAC consumption of any facility is going to be a huge contributor to the total energy usage. The following are equations that were used to reduce our total energy consumption based on a rough refrigerant mass flow rate of 60,000 kilograms per hour and a desired target temperature of roughly 21 C. For our design trade-offs, we consider the size of the system as well as the cooling capacity of the compressor. For this specific approach, we focused on the energy usage required to adequately cool and dehumidify the workspace, based on a desired target temperature of 21 C, and that the HVAC system is adequately sized for this facility. For our optimization method, we utilized unconstrained nonlinear programming. This was solved using MATLAB's fmin_con function, focusing on the humidity sensor percentage and the mass flow of the air handler. You will notice the output energy usage was around 25,856 kilowatt hours per week when minimizing the hours worked per week, and optimizing the humidity output.
The third subsystem is focused on minimizing the cost of electricity while providing adequate lighting for workers to complete their jobs. We take into account things like cost of energy, area of the factory, and the power of the lights that we selected. The objective function is focused on cost, both cost of electricity and the cost of maintenance for our lights. Our constraints are related to the utilization factor and the light loss factor, which are parameters related to how clean and efficient lights are. That will help us determine the number of lights that we need and the overall cost for that electricity and maintenance of those lights. This subsystem does have a few inherent trade-offs, namely the cost of maintenance versus energy efficiency. So the more dirt that's on top of lights, it's going to require more maintenance to wipe that off and create higher efficiency bulbs. We also have a trade-off in terms of illuminance versus the cost of electricity. So if we wanted brighter workstations, it requires more lighting, more energy for those lights. For our modeling approach, we first determine the amount of illuminance required to achieve good working conditions and to have enough light. This is kind of based off of OSHA standards for a factory floor. From there, we related the desired illuminance to the number of lamps required. We took into account also the cost of maintenance per light, trying to limit that to a certain extent so that we're not making financially bad decisions and repairing lights when we should just be replacing them. And then in the very end, we created this cost equation that relates energy to cost and to the cost of maintenance.
We determined that our variables are constrained, our constraints are nonlinear, and the variables are continuous, making this a constrained nonlinear programming problem. We utilized the fminCon function in MATLAB and were able to optimize the amount of overhead lights needed and what the utilization factor and light loss factor ratio should be. The following table shows the results from optimizing over different initial values. In this, the total cost converges to $530 with 110 lights. The utilization factor and light loss factor vary slightly with changes to initial values. This can be the case as there could be multiple local minima or due to the bounds for these two variables being small.
For the overall system, the mathematical modeling is such that we use the IDF method in MATLAB's fminCon function. The fminCon function was chosen because it is simple to decouple subsystems using estimated coupling variables. The system-level objective function is the energy cost of each subsystem. For the optimization method, the parameters are the energy usage, labor, and cost. The linking/coupling variables are the facility temperature, which is an input and output of system 3 and an input to system 2. The working time is a linking variable. The trade-offs are such that the more operating hours there are, the longer the lights are on system 3, and the longer the machines have to run in subsystem 1. Shorter time in subsystem 1 results in a decrease in the production rate. The heat generated from the light is an input to HVAC subsystem, and the total working hours as a design variable affects all subsystems.
In terms of our results for the overall optimization of our system, we found that the cost of energy, or F star, did converge, although the value was a little bit higher than expected. Most of the other design variables did also converge to the same point. However, there were a couple variances in terms of our utilization factor, light loss factor, and the number of hours that our factory would be up each week.
A sensitivity analysis was performed to see how sensitive our model is to each parameter and constraint used. In determining this, a factor of 10% was used when varying constraints and parameters to see how impactful each variable is on the final electricity cost. Among our parameters, our top three most sensitive was electricity cost, maintenance for lighting costs in the lighting subsystem, and the refrigerant constant used in the HVAC subsystem. Among the constraints, the utilization factor from the lighting subsystem, the humidity sensor percentage, and the acute compressor factor from the HVAC subsystem were the most sensitive constraints. Results of the sensitivity analysis for each parameter included in our model is shown in this table. The results of the sensitivity analysis for each constraint included in our model is shown in this table, along with an indication of whether a constraint was active in bounding the model.
After conducting the sensitivity analysis, we were able to compare the results from the individual subsystem level optimization results to the system. For subsystems 1 and 2, the cost increased, and for subsystem 3, it decreased. The coupled variable, the amount of working time, decreasing results in higher velocity and energy costs, which explains the higher subsystem 1 costs. For subsystem 2, the longer hours resulted in higher energy costs due to longer hours with HVAC system on. And for subsystem 3, the hours were less than in the separate subsystem model.
When gathering data to ensure the accuracy of the model, we looked at the current factory estimates for electricity consumption. Currently, the US EIA does not include area in their data, so instead an average value of 95.1 kilowatt-hour per feet squared per year was used based on general research. This showed that the model may be overestimating the amount of electricity, but there are a couple of reasons that would put our model higher than the average amount estimate. For one, our model assumes that the factory is solely run by electricity, while the estimate assumes that the factory may use other sources like natural gas. Additionally, Subsystem 3 takes into account maintenance costs associated with lighting, which adds to the model's electricity costs and is not included in the average amount estimate.
This project successfully implemented a constrained multi-subsystem optimization approach to reduce weekly electricity costs in a vehicle stamping factory, while maintaining the production quotas and ensuring the worker comfort. However, several opportunities exist to improve the engineering fidelity and the system integration. As an example, we can improve the model fidelity incorporating conditions with dynamic environment, such as varying the outside temperature, the daylight availability, or even the occupancy. Replacing the static efficiency and the consumption models with empirical performance curve or machine learning models. We can also improve thermodynamic modeling of the HVAC by integrating psychometric properties, latent heat, and occupancy also. For the system and boundary, we can do some enhancements, including natural gas consumption to better reflect the total energy usage. Extending the boundary to capture the supply chain related, as an example, the embedded and the raw material. We can also account for human behavior by modeling adaptive comfort ranges, shifts schedule, or even the manual overrides in the controls. At the end, the integration and real-time optimization. We can develop optimization framework that can adjust variables dynamically, integrating all the true subsystems in a co-optimization framework for the interdependencies, also including energy storage systems or demand strategies.